Welcome! In this video, we solve a beautiful number theory problem. How many integers from 2 to 100 cannot be written as a product m and n, where both m and n are greater than 1 and their greatest common divisor is 1? Let n be an integer with 2 less than or equal to n less than or equal to 100. We ask, can n be written as m times n, where both factors are greater than 1 and they share no common factor? For example, 6 equals 2 times 3 and GCD is 1, so 6 can be written this way. But numbers like 4, 7, and 27 have only one distinct prime factor, so they cannot. Let us find exactly how many such numbers exist. Here is the key idea. An integer n can be written as m times n, with m and n both greater than 1 and GCD equal to 1 if and only if n has at least two distinct prime factors. We will prove both directions of this equivalence. For the forward direction, suppose n has at least two distinct prime factors. Write n as p1 to the a1 times p2 to the a2, and so on up to pr to the ar, where r is at least 2. We split. Let m equal p1 to the a1 and n equal the remaining product. Since m and n share no prime factors, we have m and n both greater than 1, with GCD equal to 1. For the converse, suppose n equals m times n, with m and n greater than 1 and GCD equal to 1. Since GCD of m and n is 1, every prime dividing m is different from every prime dividing n. Therefore, n must have at least two distinct prime factors. Both directions are now proved. Therefore, the integers from 2 to 100 that cannot be written in the required form are exactly the prime powers, numbers of the form p to the k, where p is prime and k is at least 1. A prime power has only one distinct prime factor, so it can never be split into two coprime factors both greater than 1. Now we count. For k equals 1, the primes up to 100, there are 25. For k equals 2, p squared at most. 100 gives p in the set 2, 3, 5, 7. That is 4. For k equals 3, p cubed at most 100 gives p equals 2 or 3. That is 2. For k equals 4, p to the fourth at most 100 gives p equals 2 or 3. That is 2. For k equals 5, only p equals 2 works. That is 1. For k equals 6, again only p equals 2, that is 1. The total is 25 plus 4 plus 2 plus 2 plus 1 plus 1, which equals 35. Let us summarize the proof. First, n can be written as m times n with the coprime condition if and only if n has at least two distinct prime factors. Second, the numbers that cannot are exactly the prime powers. Third, counting prime powers up to 100 gives us 35. Therefore, the answer is 35. These are the 35 prime powers from 2 to 100. That completes our proof. Exactly 35 integers from 2 to 100 cannot be expressed as a product of two coprime factors both greater than 1. These are precisely the prime powers, a clean and elegant result from number theory. Thank you for watching. See you in the next one.